This is the second of three lectures covering section 10.2. Um, in this section, we're talking about what does it mean to compare the population means of two distinct populations or treatments. And we're going to focus in this section about calculations of confidence intervals for the difference of those population means. We've already discussed the fact that when we do two distinct samples, that the spread of the difference of those means uh, is this formula, square root variance from population one over the sample size from one divided by variance of population two divided by the sample size of two. But in truth, what usually goes on is we don't know sigma. We don't know sigma, so we settle for knowing the sample standard deviation. And instead of calling this the standard deviation of the difference of means, we call it the standard error for the difference of means. Putting this together, we know that we know that the distribution of the difference of sample means versus the difference of population means divided by the standard error gives us a t-value. And therefore, we're going to be using a t-value in order to calculate our confidence intervals for difference of means. Um, our general formula for this confidence interval is that we're going to have the difference in the sample means plus or minus this, which we call the margin of error, which is made up of two items, one of them being a T star value based on the confidence level, and then the rest of it based on the standard error of the difference of means as discussed above. As normal, we have three conditions that need to be met. The sampling needs to be made up of two independent, random samples, one from population one and one from population two. We need to know that the sampling distribution is normal, and we satisfy that by knowing that if both populations are normal or if both sample sizes are 30 or more. And then, of course, we don't want to oversample. We don't want to lose the independence. So we have the check to make sure that neither sample is any bigger than 1/10 of the population size. We're going to take this next page, talk about a sample problem, and I'll bring up an idea from days gone past. It says the Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that have survived relatively undisturbed for hundreds of years. One question of interest to foresters who study the area is how do the sizes of longleaf pines in the northern and southern halves of the forest compare? To find out, researchers took samples of 30 trees from each half and measured the diameter at breast height in centimeters. Comparative box plots of the data and summary statistics for Minitab are shown below. Question A says, based on the graph and numeric summaries, write a few sentences comparing the sizes of longleaf pines trees in the two halves of the forest. This is a classic SOX problem from way back in chapter one. So let's revive that memory. Let's talk about the shape. I'm going to mention that the longleaf pines from the northern half have a skew, because I'm seeing that this is much longer than this, and this is much longer than that, a skew right distribution for the diameter at breast height, the DBH. Whereas the long leaf pines from the southern half have a skew left distribution. All right, so we've handled the shape. What about the outliers? Well, since these are box plots and there's no separate dots, we can remark that neither distribution has outliers. What about the center? And remember, we're supposed to compare these. I'm going to say that the median for southern trees is greater than median for the northern trees. Now, I use median because it was easy to see it from the box plot. I could have used mean and came to the same conclusion. I chose median. And then what about the spread? How about we use the standard deviation for the spread? Standard deviation for northern trees is greater than standard deviation for southern trees. There we go. So that gets us through an overview, but now what's being asked of us is to find and interpret, to construct and interpret the 90% confidence interval. Four-step process, let's jump right in. Since this is a two sample, we have two distinct populations. Population one, which is going to be long leaf pines from northern part of the Wade Tract Preserve, and population two is long leaf pines from southern part of the Wade Tract Preserve. What are we measuring about these trees? And the parameter of interest is mean diameter at breast height. And that concludes our step one. Step two, plan. So let's talk about what our method name is. This is a two sample. This is a T interval because we're using T as our critical value for population mean. For our random step, we need to make sure that we say there are two random samples. For our independence check, N1, which was 30. Do we think that that's less than 1/10 of all of the trees in this old forest? I think that's a pretty safe bet. N2, which is also 30, also less than 1/10 of all the trees in that part of the forest. And then lastly, normal. They went easy on this time. N1, which is still 30, is greater than or equal to 30, which gives us that. N2, which is also 30, is greater than or equal to 30. So we meet the conditions for normality. Let's go ahead, go on to the do step. If we're using the formula, the confidence interval is x bar 1 minus x bar 2 plus or minus t star times the square root of s1 squared over n1 plus s2 squared over n2. And in this case, as if we look at the previous page, our mean for the north is 23.70. The mean for the south is 34.53 plus or minus. Now, we got to look up a t star value. We should remark here that if we're using the table, the degrees of freedom is going to be n1 minus 1, which is 29, or n2 minus 1, which is 29, whichever is less. Now, these happen to be the same. So our degrees of freedom is 29. So we're looking at 29 degrees of freedom, and we want to do a 90% confidence interval. So we'll switch over to our t-table. We'll go to 90% confidence. We'll go to 29 degrees of freedom, and we see that the t-star value is 1.699. 1.699 times the square root of 17.5 squared over 30 plus 14.26 squared over 30. And that should be enough for us to be able to go to the calculator and calculate that confidence interval. So let's go to a calculator page where I'm going to put in 23.7, 23.7 minus 34.53. I'll go with the minus sign first, 1.699 times, and then I want the square root. That's the square. Back that up. I want the square root, control square root, control division to get a fraction, and that's 17.5 squared divided by 30. And to add to that, I'll go the fraction 14.26 squared divided by 30. And we get as our lower bound negative 17.8324. And then if I go up here, I can adjust the plus minus to a plus, and we get negative 3.8276. Okay, so let's go to the calculator and see what the calculator will give us if we do the whole thing on the calculator. Adding a calculator page, menu, statistics, confidence interval, and this is a 2-sample t interval. We don't have data, we have stats. And we have 23.7, 17.5, 30, 34.53, 14.26, and 30. Oh, and we want our confidence level to be 90%. There we go. Said okay. And let's take a look what they say. They say the answer is negative 17.7238 to negative 3.93617. And you say, that's not exactly the same. Why is there such a difference? And the difference is with this calculation, the calculator used a more aggressive calculations for degrees of freedom. You can see their degrees of freedom is 55.7277. Now, the College Board finds this is perfectly acceptable, but just note that when we use a smaller degree of freedom, we get a T star value that's a little bit bigger, and therefore the confidence interval is a little wider. All right, let's finish off this problem with our conclusion, and that is with 90% confidence, we believe the difference in the true mean DBH of longleaf pines from the northern part of the Wade Preserve Tract and the true mean DBH of longleaf pines from the southern part of the Wade Preserve Tract is between, and I'll use the calculator one, negative 17.72 and negative 3.94. And those measurements were done in centimeters. So we'll include the units there. All right, let's do one more to make sure that we've got this. It says the U.S. Department of Agriculture conducted a survey to estimate the average price of wheat in July and in September of the same year. Independent random samples of wheat producers were selected for each of the 2 months. Here are summary statistics of the reported price of wheat from selected producers in dollars per bushel. So we've got, again, 2 distinct populations. So population 1, this would be wheat prices in July. Population 2, this would be wheat prices in September. And the parameter of interest in this case is mean price. Going on to the plan step, one more time with our method name, the 2 sample T interval for population mean. For our random condition, we need 2 random samples. And we have them. For our independent condition, we need that sample 1, which was 90, must be less than or equal to 1/10 of the population of all wheat prices. And we're going to assume that's true. And 2 was 45, and it needs to be less than or equal to 1/10. Again, 2. So we'll meet that condition. For our normal condition, N1, which is 90, is definitely greater than 30, so we meet that condition. N2, which is 45, is also greater than or equal to 30, so we meet that condition. On the do step, remember that our formula is x bar 1 minus x bar 2 plus or minus t star square root s1 squared over n1 plus s2 squared over n2. And in this case, we've got $2.95 minus $3.61 plus or minus. Now the T star value, if we're going with the most conservative degrees of freedom, we're going to have 45 minus 1 or 44 degrees of freedom. If we go to the table, because we're going to do a 99% confidence interval, if you go to the table, I'm looking for 99% confidence, which is that column, and 44 degrees of freedom. Well, I don't have 44 degrees of freedom. I have either 40 or 50, always going with the lower of those two numbers. We're going to go with 2.704 for our T star value. 2.704 square root 0.22 squared over 90 plus 0.19 squared over 45. All right. Going back to the calculator, let's go ahead and get that in. 295 minus 361 minus 2704 times the square root of the fraction 0.22 squared over 90 plus 0.19 squared over 45. So using the formula, our lower bound is negative 0.7590. And if we were to adjust this to a plus the margin of error, our upper bound, negative 0.5610. If we did everything on the calculator, menu, statistics, confidence interval, two sample t interval with stats, 295.22, 90, 361, 19, and sample size of 45. Oh, we want a confidence level of 99%. Oh, there's this question about pooled. We're never going to pool in our class. So pooled is always going to be no. All right. So there we have it. If we do calculator only, negative 0.7561, negative 0.5639. And again, note that these intervals are a little bit more narrow because this degree of freedom, the more aggressive degree of freedom is 100.448. Let's go ahead to that conclusion step. We're going to go ahead and say with 99% confidence, we believe the difference in the true mean price of wheat in July and the true mean price of wheat in September is between negative 0.7561 and negative 0.5649. And the units in this case were dollars per bushel. Okay, meaning that the price of wheat was about between 75 cents and 56 cents lower in September, or higher in September than they were in July. All right, so you've seen two examples of confidence intervals with two samples, and now you're ready for the homework.